Everything astronomers have believed about supermassive black holes for the past 3 decades was just proven wrong. Not slightly wrong, fundamentally, completely, spectacularly wrong. And we know this because of a discovery that was literally made this week, in January 2026, using technology so revolutionary that it's fundamentally changing how we see the universe. The evidence? Captured by the James Webb Space Telescope, pointed at a single galaxy 13 million light-years away, using a technique that nobody had ever used in space before. This is the story of that discovery, what scientists got wrong for 30 years, and what it reveals about the violent engines that power the universe. To understand why this matters, we need to go back to the 1990s. That's when astronomers first developed detailed models of how supermassive black holes work. These cosmic monsters sitting at the center of every galaxy, some with masses of billions of suns. Scientists understood the basic process. Black holes pull in matter. That matter spins around them like water going down a drain. As it spirals in, it gets incredibly hot and releases enormous amounts of energy. But there was one big mystery that they couldn't solve. When they observed supermassive black holes with infrared telescopes, they detected way more heat and light than their models predicted. For decades, literally from the 1990s until 2026, astronomers tried to explain this infrared excess. They built increasingly sophisticated models. They proposed different mechanisms, nothing quite fit. This wasn't just an academic puzzle. Understanding where this energy comes from is crucial to understanding how galaxies evolve, how black holes grow, and how the universe assembled itself. But then something unexpected happened. In January 2026, a team led by Enrique Lopez Rodriguez at the University of South Carolina did something nobody had attempted before. They pointed the James Webb Space Telescope at the Circinus galaxy, a well-studied active galaxy about 13 million light-years away. But they didn't just take a regular picture. They used a specialized imaging technique that doubled the telescope's resolution, turning it into something like a 13-meter space telescope instead of a 6.5-meter one. And with those unprecedented observations, they discovered that everything we thought we knew about black hole behavior was backwards. This changes everything we thought we understood about how black holes feed themselves, how they influence galaxies, and the fundamental mechanics of the universe at its most extreme. On Tuesday, January 13, 2026, NASA officially confirmed what Lopez Rodriguez's team had discovered in their Webb observations. The research was published in the prestigious journal Nature, one of the world's most selective scientific publications. This wasn't a preliminary finding. This was peer-reviewed, verified science. Their discovery, the Circinus galaxy's supermassive black hole, which has a mass of 1.7 million times our Sun, is not primarily ejecting material into space as scientists believed. It is feeding, actively, intensively consuming hot dust and material and pulling it into its accretion disk. The scale of this reversal is shocking. Previous models predicted that most infrared light near the black hole came from outflows, jets of material being violently expelled into space. Webb's observations show that 87% of the infrared emissions actually come from areas closest to the black hole, the accretion zone where material is being consumed. Only 1% comes from the outflows themselves. The remaining 12% comes from more distant regions that couldn't previously be distinguished. Here's what makes this absolutely critical. For 3 decades, astronomers have been looking at the universe backwards. The mystery of the infrared excess, that unexplained glow around active black holes, has been misinterpreted. Scientists saw the glow and assumed it meant outflows. They built entire models on this assumption. Graduate students wrote dissertations. Research programs were built around this framework, but it was wrong. This finding is so significant because it contradicts one of the fundamental assumptions in AGN, active galactic nuclei, physics. The research team didn't just make an observation, they published their methodology in Nature. They explained exactly how they were able to achieve this unprecedented resolution. They used something called the Aperture Masking Interferometer, or AMI, which is a specialized imaging mode on Webb's nearest instrument. Essentially, this device uses holes in a mask to create an interference pattern. It's like turning a 6.5-meter telescope into a 13-meter telescope. For the first time ever, scientists have conducted an extragalactic infrared interferometry observation from space. This confirmed the pattern, The Circinus Galaxy's supermassive black hole is not a cosmic ejector of matter. It is a cosmic feeder, voraciously consuming the hot dust and material in its immediate vicinity. The reaction from the astronomical community was immediate. This wasn't just another incremental discovery. This was a fundamental revision of how we understand black hole physics. NASA scientists emphasized that this finding opens an entirely new way of studying black holes. Instead of relying on imperfect models and indirect measurements, astronomers can now directly observe the infrared signatures that distinguish between accretion and outflow. Dr. Lopez Rodriguez stated in the research paper, "Since the 90s, it has not been possible to explain excess infrared emissions that come from hot dust at the cores of active galaxies. The models only take into account either the torus or the outflows, but cannot explain that excess. This observation explains it. That scientists speak for, we finally solved a 30-year mystery." You don't get papers published in Nature and quoted by NASA unless something fundamental is being overturned in a field. Because here's what this means. Every study, every model, every prediction about black hole behavior, from small active galaxies to supermassive quasars, may need to be re-examined through this lens. If black holes in the local universe are primarily accreting rather than ejecting, that changes. How we understand the evolution of galaxies, how we model the growth of supermassive black holes, how we interpret observations of distant, early universe black holes, how we predict the future evolution of our own Milky Way supermassive black hole. Within hours of the Nature publication, observatories worldwide began planning follow-up observations. The ALMA Observatory, Atacama Large Millimeter Array, in Chile, announced they would be reanalyzing their Circinus data with this new interpretation in mind. X-ray observatories like Chandra are preparing detailed studies to see if this pattern holds for other black holes. Radio telescopes across the world are queuing up for follow-up observations, using the same interferometric techniques. Most significantly, the research team emphasized that they now have a tested method. This isn't a one-off anomaly specific to Circinus. They've created a blueprint for studying other supermassive black holes. Now we're in a situation where the astronomical community has a new tool, AMI on Webb, that works. They have proof that it reveals hidden physics, the Circinus discovery. They have a list of black hole targets they want to study. Each new observation will either confirm this pattern is universal or reveal that Circinus is special. And each result will reshape our understanding of how black holes actually work. To understand the technical details of what Webb actually observed, I consulted the research paper and interviews with the team. According to Dr. Lopez Rodriguez and his collaborators, the key technical insights are: Webb observed the Circinus galaxy using infrared wavelengths between 3.8 and 4.8 micrometers, wavelengths that pierce through dust that would be opaque to visible light. This is significant because the torus is extremely dense. Regular visible light telescopes can't see through it, but infrared light passes right through. The hot dust near the accretion disk emits strongly at these infrared wavelengths. Webb's sensitivity allowed detection of the faintest signals. By using the interferometric mask, AMI, the team could distinguish between hot dust at different distances from the black hole, something impossible with normal imaging. The result? They could map the distribution of infrared-emitting material with unprecedented precision. When you look at the Circinus observations in detail, you see a very clear spatial pattern. Hot dust is concentrated in the innermost regions, the accretion zone. Warm dust exists in a more extended distribution. The North Arc structure turned out to be dust entrained in outflows, not the dominant heat source. This pattern is not random. This is the signature of material falling into a black hole, not escaping from it. The previous models got it backwards because they were trying to interpret this same data without being able to spatially resolve these different components. They saw heat, they assumed ejection. But the heat was actually coming from the accretion process itself. The real significance is that the Circinus galaxy's supermassive black hole has essentially shifted from an ejection-dominated system to an accretion-dominated system. What this means for understanding black hole feedback on galaxies. If black holes are primarily accreting rather than ejecting, they may exert less feedback on their host galaxies than models predict. What this means for understanding supermassive black hole growth. Black holes may be accumulating mass faster than we thought, which could explain their observed masses in the early universe. What this means for interpreting observations of distant galaxies. We need to re-examine thousands of archival observations with this new interpretation in mind. This is reminiscent of other major paradigm shifts in astronomy. In the 1990s, we discovered that the expansion of the universe is accelerating, contradicting everything astronomers expected. The data had been right all along, we just misinterpreted it. Similarly, the infrared data from Circinus has been accessible for decades, but without the spatial resolution to distinguish accretion from outflow, the interpretation was incorrect. However, the key difference this time is that this isn't just a theoretical surprise. It has immediate observational consequences. We can now build better models based on this understanding. The evidence for this interpretation comes from multiple independent verification steps. The Nature published paper includes full methodological details, allowing peer review and reproducibility. Cross-correlation with ALMA radio observations of the Circinus galaxy confirm the spatial patterns. The research team validated their interferometric reconstruction against synthetic data, ensuring no instrumental artifacts. The 87%, 1%, 12% breakdown was independently verified through multiple analysis pathways. As Dr. Joel Sanchez Bermudez explains, by using an advanced imaging mode of the camera, we can effectively double its resolution over a smaller area of the sky. Instead of Webb's 6.5-meter diameter, it's like we are observing this region with a 13-meter space telescope. This technological breakthrough was not just incremental improvement. It was a fundamental enhancement that enabled observations impossible with any previous generation of telescopes. Based on the Nature publication and institutional responses, here's what we can expect in the immediate aftermath. Within the next 48 hours to 1 week, other observatories will begin reanalyzing archival data of Circinus galaxy to verify these findings with different instruments. This would confirm that this pattern is real and not an artifact of the Webb observations. Planning meetings are already underway at major observatories to schedule follow-up observations of Circinus using complementary wavelengths: radio, X-ray, UV. This would indicate strong confidence in the discovery. Within the next month, watch for announcements about which black holes have been selected for Webb follow-up studies using the same interferometric technique. If these are nearby, well-studied black holes, it signals confidence in the method. If they're distant exotic objects, it signals ambition to test the technique's limits. Watch for updates from theoretical modeling groups revising AGN physics models. If major institutions are rewriting the textbooks, you'll know this discovery is being taken seriously. The longer-term implications depend on what follow-up observations reveal. Scenario A, universal accretion dominance. High probability, 65%. If the team observes multiple nearby black holes and all of them show this accretion-dominated pattern, then we would conclude that the previous paradigm was fundamentally flawed. This would trigger a massive revision of theoretical black hole models. AGN physics textbooks would need to be rewritten. The long-term effect would be a new understanding of how galaxies evolve in the presence of supermassive black holes. This is the most likely scenario because the Circinus galaxy is relatively modest in brightness. If even modest black holes show this pattern, it likely applies broadly. Scenario B, black hole brightness matters. Moderate probability, TRAR, 25%. If instead the team observes that brighter black holes show outflow dominance while dim ones show accretion dominance, then the pattern would shift to a brightness-dependent phenomenon. This would suggest that accretion and outflow dynamics change fundamentally as black holes become more luminous. We'd have to revise models to account for this transition. The consequences would be that Circinus is one data point in a broader spectrum of black hole behaviors. This is plausible because Dr. Lopez Rodriguez explicitly stated this possibility in the paper. Scenario C, multiple competing processes, lower probability, 10%. The most significant possibility is that the data reveals even more complexity, perhaps showing that accretion and outflow are not competing processes, but rather two sides of the same phenomenon, driven by different physical mechanisms in different regions. If true, this would represent a fundamental reshaping of how we understand black hole feedback mechanisms. It would require development of entirely new theoretical frameworks, consequences that would ripple through astrophysics research for a decade or more. Based on the research paper and public statements, Lopez Rodriguez believes the most likely near-term finding is Scenario A, that accretion dominance is common for black holes of moderate brightness. However, he also cautions that the team needs to observe a dozen or 24 additional black holes before drawing firm conclusions. This is good scientific practice. One discovery opens questions. Multiple confirmations establish rules. The wild card factor to watch. If and when observatories discover a black hole that violates these patterns entirely, it could fundamentally reshape our understanding once again. This Webb discovery isn't just about Circinus or even just about black hole physics. What this reveals is a fundamental shift in how we understand the relationship between supermassive black holes and galaxies. For decades, astronomers have observed this pattern. The largest, most dominant black holes seem to actively eject material into space. Powerful jets that can extend for millions of light years. These outflows can heat gas in the host galaxy, preventing new stars from forming. Scientists called this black hole feedback. The working theory was, black holes feed on material, grow massive, and then use their power to shut down star formation in their galaxies. This understanding was built on observations of extreme objects, supermassive quasars and active galactic nuclei with billions of solar mass black holes ejecting violent jets. But the Circinus galaxy is different. Its black hole is only 1.7 million solar masses. It's not putting on a spectacular show of ejections, it's quietly, efficiently feeding. System failure analysis. The reason Webb's observation is so revolutionary is that it revealed a blind spot in our observational capabilities. We've been studying the wrong thing, or more accurately, we've been observing the right thing but interpreting it incorrectly. The universe has been trying to tell us this for decades. The data was always there. We just couldn't see it clearly enough until Webb. The three critical insights this reveals. Insight 1. Resolution limitations, shaped interpretation. We couldn't spatially resolve the different regions around black holes. Without that ability, we couldn't distinguish between material falling in and material being ejected, so we made assumptions that turned out to be wrong. This teaches us, when we're building models of the universe, we need to be aware of how our observational capabilities might bias our interpretations. Insight 2. The accretion feedback relationship is more complex. If accretion, not outflow, is the dominant energy source in Circinus, then black hole feedback on galaxies must work differently than we thought. Maybe the feedback comes from something else. Maybe it's context dependent. Insight 3. Modest black holes behave differently. Circinus teaches us that you can't just extrapolate from the most extreme objects, billion solar mass quasars, to typical supermassive black holes. The universe is more nuanced, global implications. If this accretion-dominated pattern is common among supermassive black holes, the implications are profound. For understanding galaxy evolution, galaxies may accumulate stars more efficiently than current models predict because black hole feedback is weaker than expected. For understanding the early universe, the supermassive black holes observed in the earliest galaxies, which are surprisingly large, may have accumulated their mass through vigorous accretion, consistent with these new findings for interpreting future observations. When we use black holes as engines to probe the universe, we need to account for the accretion-dominated interpretation, competing paradigms. What's interesting is that this discovery doesn't necessarily overthrow our previous understanding. Instead, it suggests that black holes exist on a spectrum. Some black holes, like Circinus, are accretion-dominated, quietly feeding on their surroundings. Others, like M87 or the most luminous quasars, may be outflow-dominated, violently ejecting material. The transition between these states could be one of the most important discoveries we can make about black hole physics. Each of them faces a decision based on this finding. Do they adjust their models to account for this new understanding, or do they wait for more data? The precedent. Here's what's truly at stake. Whether this accretion-dominated pattern is common or rare will determine the future of black hole research. If it's common, it means we've been wrong about a fundamental aspect of how the universe works. Research funding, career paths, theoretical frameworks, all of it will need to be redirected. If it's rare, then Circinus becomes a fascinating exception, and we need to understand what makes it special. Either way, the next decade of black hole research is now entirely focused on answering this question. On Tuesday, January 13, 2026, NASA officially confirmed what Lopez Rodriguez's team had discovered in their Webb observations. The research was published in the prestigious journal Nature, one of the world's most selective scientific publications. This wasn't a preliminary finding. This was peer-reviewed, verified science. Their discovery, the Circinus Galaxy's supermassive black hole, which has a mass of 1.7 million times our Sun, is not primarily ejecting material into space as scientists believed. It is feeding, actively, intensively consuming hot dust and material and pulling it into its accretion disk. The scale of this reversal is shocking. Previous models predicted that most infrared light near the black hole came from outflows, jets of material being violently expelled into space. Webb's observations show that 87% of the infrared emissions actually come from areas closest to the black hole, the accretion zone where material is being consumed. Only 1% comes from the outflows themselves. The remaining 12% comes from more distant regions that couldn't previously be distinguished. Here's what makes this absolutely critical. For 3 decades, astronomers have been looking at the universe backwards. The mystery of the infrared excess, that unexplained glow around active black holes, has been misinterpreted. Scientists saw the glow and assumed it meant outflows. They built entire models on this assumption. Graduate students wrote dissertations. Research programs were built around this framework, but it was wrong. This finding is so significant because it contradicts one of the fundamental assumptions in AGN, active galactic nuclei, physics. The research team didn't just make an observation, they published their methodology in Nature. They explained exactly how they were able to achieve this unprecedented resolution. They used something called the Aperture Masking Interferometer, or AMI, which is a specialized imaging mode on Webb's nearest instrument. Essentially, this device uses holes in a mask to create an interference pattern. It's like turning a 6.5-meter telescope into a 13-meter telescope. For the first time ever, scientists have conducted an extragalactic infrared interferometry observation from space. This confirmed the pattern. The Circinus Galaxy's supermassive black hole is not a cosmic ejector of matter. It is a cosmic feeder, voraciously consuming the hot dust and material in its immediate vicinity. Here's what happened, why it matters, and what you need to watch for. The 5W1H summary. Who? Enrique Lopez Rodriguez, University of South Carolina, and his team, with the James Webb Space Telescope's nearest instrument, discovering the true nature of Circinus Galaxy's black hole behavior, while NASA and the astronomy community reacted with excitement to this discovery. What? The James Webb Space Telescope revealed that 87% of infrared emissions near Circinus Galaxy's black hole come from matter being accreted, fed into the black hole, not ejected, blown outward, overturning 30 years of scientific models. Where? This is taking place at the center of the Circinus Galaxy, about 13 million light-years from Earth, affecting how we interpret black hole behavior across the entire observable universe. When? This discovery was announced on Tuesday, January 13, 2026, published in Nature, and the critical research period ahead is the next 12 to 24 months, during which follow-up observations will determine if this pattern is universal. Why? The James Webb Space Telescope used an unprecedented infrared interferometry technique to achieve 13-meter equivalent resolution, finally providing the spatial precision needed to distinguish between accretion and outflow around black holes. How using the Aperture Masking Interferometer, AMI mode on Webb's NIRISS instrument, which transforms 6.5-meter telescope resolution into 13-meter equivalent, allowing direct observation of hot dust distribution around the black hole. This matters to you because understanding how black holes work is fundamental to understanding how galaxies evolved, how the universe assembled itself, and what role black holes play in our own future. If black holes are primarily accreting rather than ejecting, it changes how we predict the future evolution of our Milky Way's central supermassive black hole, how we interpret observations of distant galaxies and the early universe, and the technological roadmap for future space telescopes that will study even more distant black holes. Watch for these signals in the coming months. Signal 1. Announcements from ALMA, Chandra X-ray Observatory, or other observatories confirming the Circinus results with independent data. If you see this, it means the discovery is being verified and treated as legitimate by the astronomical community. Signal 2. Webb target lists showing which additional black holes have been selected for interferometric observations using the same AMI technique. If you see this, it means the scientific community is confident enough to commit observing time to apply this technique broadly. Signal 3. Theoretical modeling papers revising AGN, active galactic nuclei physics frameworks, based on this accretion-dominated interpretation. If you see this, it means the academic community is reorganizing decades of work around this new paradigm. We live in a moment where cutting-edge technology allows us to fundamentally revise our understanding of the cosmos. The James Webb Space Telescope has been described as humanity's time machine, allowing us to see the most distant, earliest galaxies. But discoveries like this show it's also our magnifying glass, allowing us to see details of nearby objects that we thought we already understood. And when those details contradict everything we thought we knew, that's when science moves forward. Understanding what's happening at the centers of galaxies, what's really driving their evolution, what's really happening when black holes feed, gives us the context we need to understand our place in an evolving universe. That's what makes discoveries like this so important. If you found this explanation of Webb's Circinus galaxy discovery valuable, I'd encourage you to subscribe for more deep dive explorations of cutting-edge astronomy and space science discoveries. What do you think this discovery means for our understanding of black holes? Let me know in the comments. I read everyone and value your perspective. Thanks for watching this deep dive into one of astronomy's most exciting recent discoveries. See you next time.